Hi class, this is a short video on the electrical conduction system of the heart. So this is a picture of the heart. Remember that everything is reversed in this diagram, right? Because you're looking at the anatomical position. This is the right atrium, the left atrium, the right ventricle, and the left ventricle. Um, it is important to note that the heart, if you extract it from the cavity, and it is beating in a healthy animal, that it will continue to beat. And the reason that it can continue to beat when it is separated from the central nervous system is because it has an internal pacemaker. And that pacemaker is called a sinoatrial node. It's right here. Okay, so here's the way the cardiac cycle begins. The sinoatrial node, right? The sinoatrial node, this thing right here, generates an impulse. Now that impulse is generated automatically because it has something called leaky F type, F stands for funky, sodium channels. And it's got this constant leak into the SA node. And the SA node are electrical cardiac cells. They have been modified over time, they have evolved over time, evolutionary time, to be electrical cells and not simply contractile cells like the other cells that you would find in the muscle in the ventricles of the atria. So you get this constant slow leak through these funky F-type sodium channels into the sinoatrial node cells. And when you reach threshold, you fire an action potential. You fire an action potential and those electrical signals that get generated go everywhere, because that's what electricity does. Okay, so what ends up happening is when the sinoatrial node, the pacemaker, fires, it creates a pulse. That pulse generates an electrical signal that spreads throughout both atria. So the atria, the right and the left, contract. Because the heart, unlike skeletal muscle, is a pump and relies on a sequencing. And that sequencing is that blood must come into both of the atria before it can be pumped into both of the ventricles. If that doesn't happen, you start having what are called arrhythmias, and then you can't efficiently pump blood to the body. So the signals go everywhere. Before the signal gets to the right ventricle and the left ventricle, it needs time. It needs time for all of the blood coming into the atria to fill the atria, and then for the atria to contract. So you need a delay mechanism. That delay mechanism is located in this spot right here, which is called the atrioventricular node. It is essentially another pacemaker that normally doesn't function as a pacemaker. Its primary job in a normal healthy heart is to slow the electrical impulses that are generated by the sinoatrial node from getting to the ventricles before the atria have filled and contracted. So how does this happen? There are lots and lots of gap junctions throughout ventricular and atrial muscle cells, cardiac myocytes. There are lots of gap junctions. In the AV node specifically, there are much fewer gap junctions, which means that, remember, gap junctions are a type of electrical coupling system, synapse, that will slow a signal down. In addition to having fewer gap junctions in the AV node than you would find in all of the other muscle cells throughout the heart, you also have more leaky potassium channels. And remember potassium, when we were looking at electrical signals in the nervous system, and we were thinking about current and charge, right? And we were looking at resting membrane potential. The more leaky potassium channels you have, the more potassium leaks out of the cell down its electrochemical gradient. That will hyperpolarize that area. So the AV node is hyperpolarized, right? Which means that it is much more negative, and is going to take more current to allow it to get to action potential threshold. So it's got two things that slow the signal down: fewer gap junctions and more leaky potassium channels. So while all of these electrical signals are bouncing off of the atria, triggering atrial myocardial cells to contract after the atria have filled, this area here is slowing down the signal just a few hundredths of a second so that blood can be pumped from the right atria and the left atria into the ventricles. It is slowed down. It eventually will get through. It will move down the bundle of His. And there are two bundle branches of the bundle of His. It's basically a big nerve. You can think of it as giant axon. The bundle of His transfers, bundle of His, two bundle branches, transfer its electrical current to all of these smaller axons or nerves that are called Purkinje fibers. So you go from an electrical signal in the sinoatrial node, bounces off all of the walls, allows blood to fill in the right and left atria. It allows the right and left atria to contract. That signal is slowed down by the AV node that has lots more leaky potassium channels and fewer gap junctions. The signal finally gets through, moves down the left bundle branch and the right bundle branch to the Purkinje fibers and to all of the cardiac myocytes. Once that has happened, then the right and the left ventricles contract, and then the process starts over again. So that's essentially the conduction system. Now, what happens if the SA node starts to be damaged? This interesting thing about physiological systems that have evolved over millennia is that in critical systems, and most of the physiological systems are critical, there are backups. So when one set of structures goes down, you have a backup. So imagine that the SA node sets the heart rate, and your normal heart rate is 80 beats per minute, right? So this thing fires an action potentials 80 times a minute. If this thing starts to be damaged, then, or gets completely damaged, let's say, so this is all theoretical, the AV node then has the capability to take on pacemaker qualities, and it will start to be the pacemaker. When it does it, though, because of its makeup is slightly different than this makeup. Instead of having a resting heart rate of 80, you may have a resting heart rate of 60. Now, the interesting thing about that is if you're an athlete and you took your resting heart rate down 20 beats, it's because you're in better shape and the heart is stronger. In this case, that's not true. If the AV node were to be damaged, the bundle of His branches could then become pacemakers. And now what would happen is instead of being at 60 beats per minute, your heart rate would be at about 40 beats, and then so on, and the Purkinje fibers can do the same thing. You, in a real situation, would never ever get to that. This has been done in experimental setups on animals. When the SA node starts to fail in a human being, by that point you've seen your family practitioner, you've been to a cardiologist, and you finally probably had just like many of your grandparents, had an artificial pacemaker put in that essentially takes over for the SA node. So what they have to do is they have to ablate or destroy your natural SA node. They put in a mechanical, electrical one, and then that takes over the function. And so that's just the system of backups that physiology, that nature has given you. That's it. That's all there is for the conduction system of the heart. There's obviously more information on channels in the graphs in the longer lecture, but this is essentially just a short video on the conduction system of the heart. So I hope that's been helpful. Have a great evening. Take care.